Clicca cerchi su Get Got It.
Sì.
Ok.
E invece il microfono.
No, non so se l'ha acceso il piatto.
Questo sembra acceso. Questo sembra, cioè, il verde è verde.
Si sente?
Non so se bisogna fare qualcosa. Eccolo, forse è così.
Sì. Questo, no?
No, però non c'entra
niente, il microfono va bene così, non tocca di
Muted.
Ok?
Adesso è acceso?
Si sente?
Va bene?
Ok.
Allora,
Però questo serve per...
Scusi?
Non so se
Ma no-
riusciamo per... Funziona?
Dovrebbero.
no, ma
Mi sembra.
se usiamo il microfono...
Per la sala, sì.
Beh, per la sala forse non serve.
Ah, non serve per la sala.
Se lo volete, no.
No, non serve.
Funziona, quindi non so...
Allora
Basta
spiego,
che-
magari cioè,
sì.
interferisce.
Sì.
Ok, allora magari iniziamo. Siamo pronti?
Sì.
No, non lo so.
Sì.
Vuoi fare un check di assistenza?
Andate.
Sì. Parlo, provo, si sente? Ok. Va bene, allora grazie per essere venuti qui all'ultimo appuntamento dei seminari Volterra di quest'anno. È un piacere e un onore avere Alberto Bressan che ci parlerà di modelli di traffico. E prima di lasciare la parola, volevo soltanto dire che ricominciamo, questo è l'ultimo, ma ricominciamo il prossimo anno, in autunno, non sappiamo bene quando, però ci rivedremo, forse qui e da altre parti.
Okay. So I can start. I think you hear me in this hall for sure, but okay. Well, thanks to the organizer for the invitation. Thanks to all of you for coming. So my talk will describe different models of traffic flow, and as you can see from these old and more recent photos, of course, traffic flow is a problem, has been with us for a long time and very likely will be with us for a long time. Nothing much has changed except the shape of the cars. So the first thing I want to say is that there are two very different ways, different approaches to the thinking about traffic flow. One is to study the dynamic equation, so how traffic flow evolves in time. So given initial condition, yeah, thank you. Okay. Given a condition at the present time, can we predict how the traffic will evolve in the future by solving a set of equations? Another point of view is obtained if you argue that what is the most relevant fact about traffic flow for common people? Well, it is traffic jams, of course. And traffic jams do not arise by subtle properties of mathematical equations. Basically, like in this example, they arise because too many people decide to travel on the same road at the same time. It's very simple. So you could study traffic flow from a different point of view, that is, from the point of view of decision problems, and think as a traffic pattern as a mean field problem. So optimal decision problem where a large number of drivers choose their departure time and routes to destination. And this might cause very large traffic jams. For example, the thing that's in common, all the drivers that you see in this picture is that they all made the same wrong decision, right? Okay, so in the first part of this talk, I'll just focus on dynamic equations. First, a very general, very brief survey of basic models, and then I'll describe some very recent work on the other hand. Okay, so models of traffic flow, you can divide it into particle models, where you have a large system of ODEs. Each one describes the position of a single car. And on the other hand, you have macroscopic models where you look at the partial differential equation describing the traffic density. So look at microscopic models. So you can denote by xi of t the position of the ith car, and vi of t the velocity of the ith car. And the goal is to describe how this evolves in time, writing a large system of ODEs. The simplest one would be a first-order model, where the speed of each car just depends on the distance from the car ahead. So a driver sees plenty of space in front and then goes fast. If it sees less space, it goes slower. So in this case, you would say that the velocity vi is xi dot is a function just of the distance from the car ahead. So that is about the simplest model you can think of among these particle models. Then there are also second-order models where the acceleration of the ith car depends on the speed of the ith car, the speed of the car in front, and also from the distance from the car in front. Okay, so that would give a second-order equation, one for every car, or a system. So xi dot is the velocity of the ith car, and the change in the velocity is an acceleration function that depends on these three variables. Okay, three variables. Next, let me pass to macroscopic models. In this case, the basic variable is the traffic density, which is number of cars per unit length of road. And in a basic model introduced about 70 years ago, you denote by v the velocity of cars, and you assume that this velocity is just a decreasing function of the traffic density rho alone. Okay, so typically a graph of v as a function of rho would look like this. I think you can see the cursor, right? The pointer.
Yeah.
Okay, so when the density is 0, the velocity is maximum. And when the density increases, the velocity decreases up to 0 when the cars are just bumper to bumper and they cannot move. And then at this density, the velocity is 0. So in this case, we consider the flux. The flux function is the number of cars that cross a point in space per unit time. So you fix a point x on the road, and you look at how many cars cross this point per unit time. And this is obtained as a product, the density times the velocity of the cars. Okay, so the flux is rho times v. And in a basic course on conservation law, the basic equation that you get is a conservation law for the traffic density. Oh, sorry. And it's obtained in this way. So you fix an interval AB along the road, and you look at how many cars there are inside this interval, and you say that this number of cars changes in time, of course, but only because some cars flow in from the left and other cars flow out from the right. Okay, so d by dt of the integral from a to b of rho is, of course, the integral of d rho by dt. And then you say that this is given by the influx through A minus the outflux through B. Then you apply fundamental theorem of calculus, and this is minus the integral of the gradient with respect to x of the flux. And then you realize that this quantity here, rho sub t, is integrates in the same way as f of rho sub x. So putting these together, we get that the integral from a to b of rho t plus f of rho x in dx integrates to 0 over every interval. And therefore, if you have a function that integrates to 0 on any interval, it must be the 0 function. And that's how you get this conservation law, rho t plus f of rho x is equal to 0. Okay, so that is how you get the fundamental model of traffic flow as a first-order conservation law, first-order PDE. And how do you solve this first-order PDE? Well, the standard method is the method of characteristics. In this case, characteristics are straight lines. So if you know the initial data at time t is equal to 0, you draw these characteristics, which are straight line, and the solution will be constant along these lines. The problem is that in finite time, it's quite possible that these characteristics cross each other, and that means that shocks are formed in the solution. Another way to see this is to draw the graphs of the solution at different times. And these graphs can be obtained by moving points on the graph with constant horizontal speed, and this speed is the characteristic speed that is f prime of u, right? The derivative of the flux function. So in this case, the flux function is concave down, therefore the derivative is a decreasing function of u. So points with u small travel fast, points with u big travel slowly, right? So that means if this is the initial configuration, after some times the profile of u is deformed, right? Because these points move at different speeds. So in finite time, you'll have a point where the gradient is vertical, right? And in fact, if you wait even more, you see you will get a triple valued function in this case. Of course, this doesn't make any physical sense to have a point with 3 densities. So what you do is to insert a shock. So a shock would be a point where u is discontinuous, and the position of this shock must be inserted so that the area below the graph of u has to remain constant. Okay, so in particular, these two areas here have to match to cancel each other. Okay, and that's how you construct these so-called weak solutions. So weak solution can have upward shocks also in traffic flow. What does it mean in practice? Of course, you should not think that a shock is a place where cars crash into each other. It is a place where the density of cars has a jump, right? A typical case is when you have a cross light and there is a queue in front of the cross light. So inside the queue, the cars are packed bumper to bumper, so the density is very high, and before the end of the queue, of course, the cars keep flowing, keep coming, and the density is much lower. So the end of the queue would be the position of a shock, and this shock moves backward in time because the queue becomes longer, of course, while, of course, all the cars only move forwards. Okay. All right, so this is the end of my crash course on conservation law. Now I want to come to more recent work, and the main motivation is stop-and-go waves on the highway. So that's something that has been observed many times. And the fact is that when the density of cars is sufficiently high, you see that this spontaneous oscillation in traffic density occurs. So you initially have a density which is almost constant, and then later you see a density that keeps oscillating. So we have regions where the density is high. So like stop, if cars has almost to stop or slow down a lot, and regions where the density is low, so the cars go fast. Okay. Now, the point is that there is no way a scalar conservation law can explain or can predict this type of traffic stop-and-go waves because it has the comparison property. That is, if you have an initial data which is between two constant states, that is between u minus and u plus initially, then for all positive time by comparison, it will always be between u minus and u plus. So definitely the solution will not look like the one on the right, which has wider oscillations. Okay. So how can we modify our model to account for the emergence of these stop-and-go waves? So my goal here is just to find the simplest possible model that accounts for this. I'm not asking for something which is accurate or physically or close to observation, just the simplest mathematical model. And I want to say that this can be achieved by a single scalar conservation law, but with discontinuous flux. So before I do this, let me first survey a large chunk of literature. So I should point out that in the area of conservation law, when you talk about conservation law with discontinuous flux, almost everyone thinks about a flux which is discontinuous as a function of x. And this is very common. Think of a highway where on a certain stretch, you have two lanes. And then at some point, there are works along the highway. So there is only one lane and the other lane is closed. Okay. And of course, here on the left, you will have a certain flux function with two lanes. And then on the right, you have only one lane. You have a completely different flux function. Okay. So you would have a discontinuous function f, but discontinuous with respect to x. And this problem has been studied first by Gimse and Risebro, which I think is the first and best model paper on this, where they correctly identified the vanishing viscosity limit for this type of equation. And then it became very popular, and a lot of other papers appeared on this type of problem. So it's a very rich subject. The type of conservation law with discontinuous flux I'm thinking about now is completely different. Indeed, I think of something which is discontinuous, but as a function of u sub x, as the gradient. And the motivation for this is that there are two driving modes. One is when you keep the foot on the gas pedal, and another is when you keep your foot on the brake pedal, right? And you can think that in these two modes, you have a slightly different flux functions, right? So gas pedal essentially corresponds to an acceleration mode. So that means that ux is less than 0. So you look ahead and you see that the density of cars is decreasing. So you have fewer cars in front of you, so you can accelerate, right? On the other hand, if you see a lot of cars in front of you, then you should decelerate, right? And that gives a conservation law really with two flux function, and you switch from one to the other depending on the gradient of the solution. And here I draw three different possibilities on how this function f and g can look relative to each other, right? So there is one setting which I call the stable one, where f is less than g, another which is unstable when f is bigger than g, and then there is the mixed case when the graph of f and g intersect, and this still has not been fully studied. Okay, now, why we call f less than g the stable case? Okay, let me explain this. So let's say I have an initial data, which is piecewise monotone. So it increases up to x1, then it decreases, and then it increases again. Okay, so it will have a local maximum here and a local minimum here. So near a local maximum, what happens? Well, here we are assuming f less than g. Okay, so it means that on the left, the flux is small. On the right, the flux is big. So a lot of mass is coming in. Sorry, a little bit of mass is coming in, and a lot of mass is going out, right? So it means that if you look at the total mass in a neighborhood of x1, it's decreasing. Okay. The opposite happens next to a local minimum, because in here, on the left, the flux is g, and on the right, the flux is f. So a lot of mass is coming in, and little mass is going out. Okay. So in this case, the total amount of mass in a neighborhood of x2 will increase, right? So local maxima decrease and local minima increase. So you would expect that in this case, oscillation will be damped and the solution should be stable, right? And in fact, well, this is a purely heuristic argument, right? But in fact, we can prove a rigorous result in this case. So if f is strictly less than g, then this conservation law with two fluxes yields a contractive semigroup in L1. So for every initial data in L1, we can associate a unique solution forward in time and two solutions. The L1 distance between two solutions is non-increasing in time. Okay? And in fact, one can also prove that the semigroup are unique limit of vanishing viscosity approximation. Okay. So we do not really think of entropy condition, because for this type of equations, it doesn't really make much sense to think about an entropy where the flux depends on u sub x. Right? But it makes sense to think of this as limit of smooth approximation with a small viscosity, and the limit of this approximation is unique and is a contractive semigroup. Okay, on the other hand, we have this unstable case where g is less than f, and if you repeat this analysis as before, let's say I have an initial data which is increasing, then decreasing, then increasing again. Well, at the point where you have a local maximum, you see if f is bigger than g, a lot of mass comes in and little mass goes out. Okay? So corresponding to a local max, the total amount of mass in a neighborhood of x1 increases. So we expect that local maximum will increase even more and local minimum will decrease. Okay, so oscillation will be amplified in this case, and that's why we expect solution to be unstable. Of course, this again is a very heuristic argument, but in fact, it turns out that in this case, the Cauchy problem can have multiple solutions, and I'll show you right away how to construct multiple solutions for the same constant initial data, right? So let's take an initial data with flux F, which is constantly equal to U naught. Let's say here's U naught. Let's draw the graph of F and the graph of G. And then from this point, F of U naught, we can send two tangent lines to the graph of G, and these will cross or touch the graph of G at 2 points. One is, let's say, W minus, the other will be at W plus, okay? In this case, we can construct a new solution that has this double spike in this way. So first, you insert an upward shock from U naught to W plus, and then you have a downward rarefaction from W plus to W minus, and then you have another upward shock from W minus to U naught. Okay, so you jump up, then you go down, and then you jump up again. And if you look at the speed of these two shocks, well, the first shock, this one goes with what speed? The speed is the slope of this segment here. So in this case, as I've drawn it, the slope is negative, so this will go backwards. And the second shock will go with the slope of this segment, Q minus P, which is positive, so this will move forward. So if you wait some time, this spike will get bigger and bigger. So, and this would be just a second solution. And you can insert as many solutions as you want, because you can decide any time t and any point x where you want to produce your spike. Okay. So now I come to a key point of this talk, that is, in the community of hyperbolic problems, when you see an evolution equation, the first thing we are concerned about is this well posed, right? Because if it's not well posed, you cannot use it to predict the future looking in terms of the present. So it's good for nothing, this equation. So there must be something wrong in the modeling. But in this case, it's quite an important feature, the fact that the equations support infinitely many solutions, because now we can put a probability distribution on the set of all solutions. And that gives an interesting new stochastic process whose sample paths are solution to a conservation law, right? So how can you do that? Well, we just think that these points and times, Tj, Ti, and Xi, where the new spikes are generated, these are random points with Poisson distribution. Okay? So we consider a random sequence of times, T1, T2, T3, with Ti minus 1 independent, identically distributed Poisson random variables. And then we consider a random sequence of points on the road. And here, for simplicity, I think that the initial data is constant and U is spatially periodic. So I want to work on a bounded interval. So L can be as big as I want, in fact. So it's not the problem. Okay. And then for each I, if theta of Ti xi is 1, so if the flux at this random point is F, then I can generate a new spike in the solution. if the flux is G, then I cannot generate any spike. So I just prolong the solution as before. Okay. And what happens? Well, it turns out that with this model, well, you see some spike, but in the long run, everything decays to a constant state. So as a stochastic process, it's rather boring in a sense, because everything pretty soon decays to a constant solution. So nothing interesting going on, right? So a more interesting model is achieved if this switching is not when ux is bigger than 0 or less than 0, but it is when ux is bigger than some value minus delta. It could be very close to 0, in fact, or ux is less than minus delta. What is the difference? Qualitatively, it makes a huge difference because, you see, let's start with an initial spike, which is this one, and then this spike amplifies and the gradient decays by Olenek estimate, basically, because G is concave downs, genuinely nonlinear. And then after some time, the gradient decays like 1 over t. And so at some point, the gradient becomes bigger than minus delta. So this flux, instead of being G, it switches to F. Okay, now I have a profile where the flux is always F, and therefore I can generate a new spike inside the old ones. And this process can repeat over and over. Okay. And okay, now it could be the right time for a. Okay, so do you see this animation? It should start. Can you make it start? Or it should produce. No, the time is. It's not starting. Sorry. Can you see? I only see the first snapshot. It's a MP4. It's working. No. No. Sorry.
Questa qui o...
Sì, è quella giusta. Ma,
forse no, abbiamo caricato un po' prima.
sì. No, and then it's. Okay, this is just the first slide. No, it should be. Well, I can show.
And uploading.
Uploading.
Yeah, it's uploading because it's not uploaded before. So we just charged, but I don't know. Please, they're not very fast.
Well, otherwise I can just show the final.
Maybe I'm wrong.
Well, no, I can just show the slide. If you can go back to the previous slides I had before. No? Okay. This is okay. So this would be a snapshot of how the solution looks with a loss of spike after a long time. The lower graphs indicates the one on the left is the number of jumps as a function of time. So initially start with 0 jumps, and then of course more and more jumps, more shocks occur. But the fact is the total number of shocks does not go to infinity because they merge into each other. So more and more are created, but then they merge into each other, and then the number decreases. On the left, on the right, you see two graphs. The solid graph is the average velocity of cars, and the dotted line is the average acceleration of cars. So corresponding to new spikes, so the more spikes there are, the lower is the average velocity, and the higher is the average acceleration, because cars have to accelerate and slow down and accelerate even more. Okay, so that's how it looks like a typical example of these solutions. Okay, so if I have still a little bit of time to talk about this. So this is an interesting Markov process, and there are lots of things that you can prove about this Markov process. For example, we can show a bound on the expected total variation of the profile. So total variation would be the total variation of this profile here on an interval 0L, of course, right? How do we bound this? Well, at some time t, you look at the previous time at which a spike has been created. So let's say tk, tk minus 1, tk minus 2, tk minus 3, and so on. Okay, so what would be the worst case scenario? How much could be the total amount of oscillations at time t? Well, there is, if sigma is the maximum size of a spike, well, there is the spike produced very recently at time tk, which is this one. This is extremely steep. It doesn't take almost any space. And then there is the one produced at time tk minus 1, and this takes up some space. It's proportional to t minus tk minus 1, because this, once they are produced, they expand, right? And then there is the spike produced at time tk minus 2, which would be this one. That takes up even more space. Then the one constructed tk minus 3 takes up even more space, and so on. Now, the total amount of space is L, because that's the length of the road. And then the total variation is the number of spikes that you can fit inside an interval 0L, taking into account that if you take older and older spikes, they take up more and more space. At some point, you cannot fit any more of these spikes, right? And once you make a change of variables, clean up a bit this formula, what you get is the following. So the following problem: you consider a random sequence of independent, identically distributed Poisson random variable, and here the intensity is mu, where mu is related to the lambda we had before, but lambda times the length of the road divided by the maximum spike, and the beta, which is the coefficient of nonlinearity. okay, the second derivative of the flux. And this determines a discrete random variable. So given a sequence of these random variables, θ1, θ2, θ3, and so on, then I construct another random variable with integer values, which is the following. It's the minimum n such that this sum is greater or equal than 1. So you take θ1 plus 2 θ2 plus 3 θ3 and so on until the sum passed beyond 1. Okay, that you stop. So the question...
I mean, this sigma is the new variable you have introduced with respect to the previous model.
Yes, sigma would be the largest size of these spikes.
The picture is non-trivial because the sigma is bigger than 0, or not? I mean, comparing with the previous...
Yes, in fact. Yeah. Sigma can be large. L, in particular, can be very large. Is the size of the rod. That will be large. Beta, well, beta be either small or large, but yeah. So you have these discrete random variables, and you count how many terms you have to sum until the value of this sum is greater than 1. Okay. And that's a new type of random variable. I've personally not been able to find it on books on probability theory. It's easy to show that the expected value of this random variable is finite. And it turns out that the expected value of the total variation of the solution u of t is bounded by 2 sigma times the expected value of n plus 1. So in terms of this discrete random variable, you can estimate the expected total variation of u of t. Well, there are other things that we can prove, so let me just give you a summary of results. So for every sequence of times and points, we can construct a unique solution to the conservation law with 2 fluxes, where the new spikes are generated at these points if the flux is F. If the flux is G, then nothing happens. And then we can prove bounds on the expected total variation on the average velocity of cars. This bound is deterministic because it comes from Jensen's inequality, nothing more than that. Then we have a bound on the expected average acceleration and also on the expected number of shocks in the solution. And when I say they are bounded, these are bounded independently of time. That is the non-trivial part of the thing, right? Because the shocks, of course, more and more shocks are generated, but then these shocks impinge on each other, so their number decreases. And then we can also prove that this Markov process admits a unique stationary probability distribution, and it's recurrent and ergodic. And this relies on some old criterion by Harris. I think it's in the 1950s. And there is a very recent work by Martin Heirer that gives a very elegant proof of this older result. And that's what we use. Okay, so that's about what I wanted to say about the modeling. Next, I want briefly to talk about optimal decision problems. So it's a completely different way of thinking about traffic flow. So we can look at globally optimal traffic patterns, so where departure rates are assigned by a central planner, or Nash equilibrium solution where each driver minimizes his own cost given the overall traffic pattern. Okay, so how do we formulate a problem like this? Well, simplest setting, let's say we have car drivers that starts from a location A, think of a residential neighborhood, and they need to reach a destination B, like the center of the city, a working place at a given time t. And there is a cost for departing early because nobody likes to wake up early in the morning and start driving. And the cost psi depending on the arrival time if you arrive late at work, right? So this fee, could be the departure cost, and this might be the arrival cost. Okay. So each driver, of course, has the sum of these two costs, and there is an elementary solution. So if the travel time delta t is constant, so the arrival time would be the departure time plus delta t fixed. Well, this is a calculus 1 problem, right? You have to minimize this function of just one variable, the departure time. So minimize with respect to t, phi of t plus psi of t plus delta t, and that's all. Of course, the fact is that if everyone follows exactly this same optimal strategy, then a big traffic jam is created because everybody goes exactly at the same time, and the optimal strategy is, well, far from optimal, right? Because a traffic jam is created. So the speed of cars depends on the traffic density, and we have to keep this in mind in our model. Okay, so what could be an optimization problem for traffic flow? Let's say K is the total number of drivers, total number of cars that have to depart, and we have a departure cost and an arrival cost. And now we have to choose a departure rate so that the solution to this conservation law minimizes the sum of all the costs to all the drivers. This is a global optimization problem, and that would be a problem for a central plan. Okay. So what are the results? Well, this is a picture. So they start at 0, x is equal 0. They arrive at x is equal L at the end of the road, right? And we have a departure rate, which is this, let's say, u bar of t. So in this picture, it means that the first driver departs at this time here, then more and more driver depart in this time interval. The last one departs at this time here. And this is the arrival rate. And the total cost would be, of course, the departure cost times the rate of departure plus the arrival cost times the rate of arrival. But the rate of the arrival is obtained by solving a conservation law, of course. And one result we could prove quite some years ago with my former student, K. Han, in Penn State. Now he is a big transportation engineer in China, actually. So for every K, the total number of drivers, there exists a unique departure rate U bar, total amount of cars is K, and minimizes this total cost. Now, and this globally optimal solution can be easily characterized. And the property is that if you look at characteristics of the solution, along each characteristic, the departure cost here at the initial time plus the arrival cost at the terminal time is constant. It does not depend on the different characteristics. Okay? So that's a simple way that allows you to construct this optimal solution. Okay? But of course, this is a globally optimal solution. And if you look at what is the cost paid by individual drivers, that's not at all constant, because the driver who starts very early in the morning, he pays a lot. The last one pays also a lot, and the one that departs at an intermediate time, in the middle, they pay less. So here there is like this central planner that forces some drivers to depart early so that they leave the road empty for the one that will come later, right? And this driver may not be happy at all. Right? So another type of definition of concept of solution would be the Nash equilibrium, where no driver can reduce his own cost by choosing a different departure time. So that means in this case, all drivers pay the same cost. Okay. So in this, how is this characterized? Well, there is a constant such that for every particle lines, the initial cost plus the terminal cost is constant. Okay. So the difference between this picture and the previous one is that these are particle lines, so trajectory of individual driver. These are not characteristic. In fact, these are not straight lines, as you can see. Right? So again, we can prove that for every k positive, the total amount of cars, there exists a unique departure rate, u bar, where the integral of u bar is k, so everybody starts sooner or later, and all drivers pay exactly the same cost, right? So this could be the departure rate, and phi is the cost of drivers as a function of the departure rate. Okay. On the support of u bar, phi is constant. And then one can also look at or compare these Pareto optimal and Nash equilibrium. And you can see by numerical simulation, they are very different. So here on the left, the lower graph is the density of departure in a Nash equilibrium. And the upper graph, of course, is a constant function, which is the cost paid by drivers departing at different times. In the second graph, this is the departure rate of drivers in a globally optimal solution, and this is the cost for single drivers departing at different times. And of course, this is not at all the constant. Okay, so for the Pareto optimal, we can prove, in fact, that the departure rate is smooth, and the solution also remains always smooth, never develops shocks. Okay. On the other hand, quite recently, in fact, we proved that for a Nash equilibrium, for generic departure and arrival cost, the departure rate has downward jumps. So this numerical simulation with jumps downward, in fact, it's generic. It's not a random thing. And so for a open dense set of C2 costs, you have a Nash equilibrium which is not smooth. Okay. Another interesting open problems, I would say, is the dynamic stability of this Nash equilibrium. So what is the point here? Let's say that one day you depart at a certain time and you run into a horrible traffic jam. So the next day you will change your departure time, right? Maybe I can do better if I depart maybe somewhat earlier. Okay. But of course, also the other driver may have the same idea, and then you might still run into a traffic jam the next day, and so on and so forth. Okay. So we could devise an evolution equation for this departure rate. Okay. Of course, we can do it thinking theta as a discrete variable, but then we can think also theta as a continuum variable. So let me call u bar of t theta is the rate of departure at time t on day theta. And this might change from one day to the next. And then let's call phi of t theta is the cost to a driver starting at time t on day theta. Okay. So if at some day phi of t were constant, then it's a Nash equilibrium, everybody is happy, nobody has any reason to change his departure time, and that would be an equilibrium point for this evolution equation. So there are two different types of evolution you might think of. One is gradient flow, right? So you look at this function phi of t. So the total cost as a function of the departure time. And if this is not constant, well, the driver that departs at one time where d phi by dt is not zero, he might try to move his departure time in the direction of the negative gradient, right? So it would continuously change his departure time, trying to go downward. Another model, it's a case where driver just jump from one time to another time. So they just look, for example, here, the one that initially departs at time s looks, well, there are many other times where the cost will be lower. So I'll jump to one of these other time and with probability proportional to the difference in cost, right? It makes sense. So, and this leads to an evolution equation where for each time t, the density of drivers that depart at time t may increase because other drivers from at time s will move at time t, and decrease because drivers that depart at time t, they will find some other time which is even better and will change. Okay. So in both of these cases, we have some evolution equations. So natural question is, does this evolution problem has unique solution? Is this well posed again? And what we can prove very recently, in fact, that for model 2, where they jump, the model 2 is the one defined in terms of integrals. Yes, in this case, the evolution equation has a unique solution, is well posed, and the departure rate has uniformly bounded support. Well, that's quite reasonable. You don't expect drivers to start at times very early or very late where the cost is very big. That's all. However, this is still an open problem for model 1, that is gradient flow. And it's difficult because it leads to a scalar conservation law with discontinuous and non-local flux. I mean, people that are working this area, they know that discontinuous flux is hard, non-local flux is hard. When you put them together, it's a nightmare, right? So that's, and the question too is, this evolution equation that has the Nash equilibrium as a steady state, does it eventually converge to this Nash equilibrium or not? And well, I had some numerical stimulation going back to 2011, then, and they would indicate that Nash equilibrium is unstable, and now it's not clear what causes instability or if there is a chaotic dynamic. So the numerical simulation would indicate a chaotic dynamic, so there is kind of a strange attractor, which is compact, but I mean, this is purely numerical. At that time, we didn't even have the existence of solution for this evolution equation. Okay, so, and so this is another open problem. Well, if I could, I would show you animations.
Yeah.
And if not, well, that would be the end. Okay.
I can try to.
Yeah, okay. If you have the animation, okay, that would be. So in this animation, we start with initial data which correspond to the Pareto optimal, so which is globally optimal for all solutions. The sum of all the cost is the minimum, but drivers pay different costs, so some of them are not happy, and therefore they keep changing. So, okay, so in this animation, I can already tell you, the lower picture is the density of departure. The upper picture is the cost. So corresponding to local minimum of the cost, you will see that the density of departure increases because everyone tries to go close to a local minimum where the cost is minimal. But then if everybody wants to depart at the same time, then jam is created and the local minimum is no longer an optimal solution, a minimum. So that's why it keeps moving, and apparently it does not converge to anything. Okay, so well, if you have it, we can look at that. They are also, they can be found on my webpage. This might be another one, but the animation, we still see just one. Okay, well, it's all right. But then I can just stop here, and thanks for the attention.
Any question or comment?
I mean,
Yeah.
here, in some sense, the microscopic equations are, are describing the microscopic systems. So I'm asking whether it's meaningful to take a different scale in which the equations are macroscopic description of some more microscopic models. In some sense, you just mentioned that is here the entropy solutions doesn't make sense because there is no local equilibrium.
In the unstable cases, these new models where the flux depend on use of X, no, at the moment there is nothing. There is quite some literature on the limit. So you start with particle models, you let the size of each car go to 0, you let the number of cars go to infinity, and you recover various types of conservation laws. This has been studied. In fact, quite recently, there are results in this direction.
And there are local equilibrium, the equivalent of thermal equilibrium for gas. There are some notion of local equilibrium for the traffic, for car traffic, no?
No, this I would not say because it's just if you look at the ODE, the initial ODEs, which I had on the very first slides. You take a limit of these ODEs, like this one. This is the simplest one.
Yes.
You let the number of cars go to 0, and then you see that the velocity, the density of cars is 1 over this distance between one and the car ahead, and then this is how you get the flux, right? Yeah. And I guess one can do this also in these second-order models. Then you get things. Well, there are also conservation law, system of conservation law now, because it's second order, which, well, they work so-so, but sometimes, well, the first model, they had car going backwards, so was not very efficient. But yeah, on the other hand, for these new models where you have dependence on use of X, this has not been done at all. So there is no corresponding model, discrete model of this form, particle models. It could be studied, I guess, but has not been done yet because it's all extremely recent.
Yeah. For instance, the total lattice would fall in this class.
What, the total?
The total lattice. The model, that model with a special choice of B. No, the other one, the second
This
case.
one.
With a special choice of the function A.
Yes.
So total lattice has no V dependence, only an exponential. The other thing. It's interesting because it has solitons and can be solved exactly.
Yeah. Well, the problem with this, I would say, these are well posed. So when we model stop and go waves, by their nature, these are probabilistic. You cannot predict exactly the time and place where a stop and go wave will be formed, as you cannot predict the time and place where an accident will happen. So with this second order model, you can predict, or you can model the shape of these waves, but not how they are generated or how they are dissipated, let's say. That's a difference.
Okay, if not, then thanks a lot.
Okay.